Umbilical cord blood gases and lactate at birth. Photosynthesis by plants enabled oxygenation of Earth, by which light energy could be stored as chemical energy, and animals could thrive and grow larger. However, the benefits of oxygenation had a price, the threat of hypoxia. Glucose is the main fetal energy source. By glycolysis, 2 ATPs are created when converted to pyruvate. By the aerobic pathway in the citric acid cycle, up to 36 more ATPs are created. In the absence of oxygen, pyruvate must enter the anaerobic pathway, and lactate and hydrogen ions are created, but no more ATPs. In the absence of oxygen, anaerobic metabolism eventually results in metabolic acidosis. Hypoxia develops in 3 steps. First, hypoxemia with low oxygen in blood, then hypoxia with low oxygen in peripheral tissues, and finally asphyxia with affection of vital organs such as the brain and heart. Asphyxia with metabolic acidosis is a serious condition that could cause irreversible organ damages. Umbilical cord blood gases at birth are thus our best objective proxies of the recent intrauterine oxygenation. Contrary to common beliefs, about 75% of encephalopathies and 90% of cerebral palsies are not associated with intrapartum hypoxia. The normal metabolism always results in production of hydrogen ions. However, if these little green creatures take over, we have a problem. We have metabolic acidosis. They must be neutralized. It is mainly bicarbonate in plasma and hemoglobin in erythrocytes that buffer and neutralize the hydrogen ions. By bicarbonate buffering, carbonic acid is created, and carbonic acid is then split to water and carbon dioxide, which easily cross the placenta to the mother. To understand the difference between metabolic and respiratory acidosis, it is good to remember the Henderson-Hasselbalch equation. An increase in hydrogen ion concentration will result in consumption of bicarbonate buffer, and pH will decrease. An increase in PCO2 will as well result in a decrease in pH. In this way, metabolic acidosis develops by an increase in hydrogen ion concentration and running short of bicarbonate. Respiratory acidosis is not caused by hypoxia, but by an accumulation of CO2. Base excess is the negative value of base deficit, but in perinatal medicine we rather say base deficit, because in the newborn base excess is most often negative. Base deficit reflects the metabolic component of a low pH. It can be calculated in blood or in the extracellular fluid, where base deficit in extracellular fluid is less influenced by PCO2 and therefore better represents the metabolic component. This slide shows 3 important things. First, that BD varies with gestational age, as do pH and other blood gases and lactate. Number 2, that BD in blood is higher than in the extracellular fluid. And 3, that different BD values are achieved from different blood gas analyzers. The question is, do such differences matter? Let's see. Metabolic acidosis is commonly defined as a cord artery pH below 7 and a BD above 12, and severe metabolic acidosis as BD above 16. This is a comparison we made between 2 different equations of BD in blood. As you can see, the plottings deviate from the line of identity. As a result, a BD value of 12 will result in a 2 millimole per liter difference in reciprocal comparisons. We also calculated BD in blood and in extracellular fluid with equations from 4 different analyzers and found an inter-analyzer difference of values above 12 with up to 426%. So there is no doubt that such differences are important. It is therefore important to define which fluid compartment is used, blood or extracellular fluid, and which equation when calculating base deficit. That is commonly overlooked even by high standard authorities. Since the cord arteries carry blood from the fetus to the placenta, it is arterial blood that best reflects the fetal acid-base status. We now therefore need to validate the arterial sample by showing it has a lower pH and higher PCO2 than venous blood. To make a long story short, to validate cord samples, the veno-arterial pH difference should be 0.02 or larger. Delayed cord clamping allows transfusion of blood from the placenta to the baby, which has beneficial effects on hemoglobin and iron stores in the infant. However, delayed cord clamping and blood sampling will distort blood gas values towards acidity and occasionally result in a false diagnosis of acidosis. That is an effect of the centralized circulation during labor, giving priority to vital organs. Acidic metabolites are then accumulated in the hypoperfused peripheral tissues. After birth, when the baby starts to be active, these acidic metabolites flood into the central circulation and further to the cord. This we call hidden acidosis. Hidden acidosis may result in falsely acidic cord blood gas values. The down-regulated peripheral circulation is recognized as acrocyanosis in the newborn. It is not difficult to solve the issues associated with early and late cord clamping. Simply puncture the unclamped and still pulsating cord without delay and draw the blood. Different cutoff limits for a normal pH are used in the literature, and there is not yet any global consensus. However, from a literature survey I performed, there is good evidence that in deliveries exposed to labor contractions, the lower limit at mean -2 standard deviations is 7.10. Similarly, the lower cutoff limit is 7.13 at planned cesarean section. Since lactate increases with advancing gestational and age, it is not possible to set a fixed cutoff covering all gestational ages. Reasonable cutoffs are 9 millimole per liter at 37 weeks, 10 at 39-40 weeks, and 11 at 42 weeks. As long as we don't have any consensus on which base deficit equation to use, we cannot settle any accurate reference values. Until we have decided, we will continue to lean on the wisdom of James Lowe. Thank you for your attention.